In other words, until a high frequency light starts to move out of phase, created there, with the high frequency light created here. So phase matching light in any ordinary nonlinear process works here as well. It's more difficult here because the frequency differences are much greater. Effectively, X-ray is nothing, and it's not true for visible light, of course, which is highly sensitive to electrons and especially ionization.
So it's not bosonic enhancement. It's not bosonic enhancement in this case. It's kind of like it's coherence in time.
This is just coherence, just like in ordinary harmonic, I should say. It's really very similar to second harmonic. But it's not a single atom process. You can understand so much of a single atom that it's easy not to say. I'm not sure if I'll go through the whole talk without saying this. And everybody in the audience would say, well, who would care? I got an attosecond pulse from one single atom. What's the chances? There's no interest. It becomes interesting because I can have a macroscopic number of atoms doing exactly the same thing and giving me that. So conversion efficiency, maybe this is important to say. Conversion efficiencies in the region of 100 eV, 50 to 100 eV, in things like argon, can be pushed to about 10 to the minus 5. That is fundamental. It's not bad. It's not great, but it's not bad. If you go more extreme, if you go to high harmonics and go to a kilovolt, I think the numbers are not clear yet, but it's not as good. It's clear. And there's a lot of work trying to optimize this. So in the region of 50 to 100 eV, you're propagating along, the XUV is propagating along, but you think about 100 eV photon is ionizing argon atoms around, or even argon ions is ionizing and being absorbed. And so eventually you get to a point where the absorption of this radiation is equivalent to what's being added. And that's the best you can do. Your absorption limited, and that is about 10 to the minus 5 conversion efficiency in that region in argon. And we can reach that in argon and some systems. We cannot reach that in helium like that. And whether we will be able to or not is not clear. Okay, this is, I think, my last, or second to the last slide, and I think I definitely have to be done. So the next part is, how do you get an attosecond pulse? It's more specialized. I leave that for the next, my next lecture, which is tomorrow, I think, at times. There are a number of gating techniques. I won't describe them here. There are 5 of them listed here, and I'll start out, not exactly here, but not very far from here. And I'll tell you, I'll pick one and show you how it works, and how we create a real attosecond pulse, and then how we measure. So next lecture, making, measuring, controlling attosecond pulse. Thank you.
Thank you. Here you go. You have your first assignment, right? Calculating classical trajectories for these electrons as they come out in a linear or a circular pulse, right?
And the autocorrelation.
And the autocorrelation function.
Starting with.
And Paul would like to see the results this evening.
That's a good idea. I didn't think about that. That's a good idea.
So,
questions? Hopefully not everybody gives you assignments, because you have a lot of things to do this afternoon. Yes, they do. Any questions? Questions, please.
When we do frog and we find, let's say, close duration, is that completely unique?
Yes, I'm not an expert who says this. I have read the experts who do say this, yes. You can get, you can show a theorem that the solutions, that it's only a set of measures zero. So there is a unique or essentially unique solution, yes. There is a unique solution.
You described something of the talk in the harmonic generation variation in your case of what is like. So can you describe one more time?
I can't, but I didn't quite understand every aspect of your question. Could you please repeat? Then I will try to.
So you, so in your three-step model slide, you mentioned how there is a from net to that is, and you mentioned something.
Can I tell you why that is the case?
Yeah.
Yes. I will tell you, and I will point you out to go back and work it out. So let me do that. That's not back very far, so go back.
There is a white ball. You need a white ball.
I don't know if that's easier or not. Let me try to do it with my hands, and I can go to the whiteboard if it's useful. When you do classical trajectories tonight, and you release an electron at all possible phases of the pulse, you will find first that if you do it simply, turn off the Coulomb potential after the electron goes, so to keep it simple. So let the electron propagate after it's released, just in vacuum. Then you'll find that anytime after the peak of the field and before the zero crossing, will allow recollision. In fact, you'll find that the electron will go out and come back and cross its initial position. You will also find that there are two ways or two times when an electron can go back with the same energy. You can see this actually in your mind. Let's imagine an electron born at the peak of the field. It's pulled away from the quarter cycle. Its momentum carries it the next quarter of the cycle against the field. It's driven back for a quarter of a cycle, gaining energy again. And its momentum carries it to the ion just as the field reaches its peak and it goes back. So it collides with zero velocity if it's born here. So now in between it'll go up. You can trust me. Let's think about the one right here at 90 degrees. It barely gets away before the field changes direction and gets pulled back again. There's no time to pick up energy, so it collides with zero velocity. So the curve is like this. So the electrons born here will return back more energy, more energy, more energy. They reach a peak, which comes at the zero crossing here, approximately, and then they turn off again. It turns out that experimentally we can choose to look at these ones, the ones born late, and almost everybody does. And so you get ones born late and colliding early, and they collide with lower energy, working their way up the curve. Born a little earlier, colliding a little late with more energy, born by being born even a little earlier still and colliding at the optimum time. And this gives you a time frequency mapping of what you would see in the experiment. And that's exactly what you see. Is that clear? Good. Yes?
Okay, how far can we go to then the time delay of these two pulses?
How can you make two?
How far can we how far can we go to the time delay? How short can the time delay be?
I think you're thinking about pump probe that I described earlier. Invisible.
Yes.
In that case, I can bring them right superimposed. If you're thinking about back here where I talked about, you can do spectroscopy. There's no reason why that can't go right down essentially to zero. The two pulses could overlap if they wish. Now, maybe it's not easy to understand when the two pulses are superimposed what you're seeing. Maybe it is, but maybe it isn't. We can make pulses, individual pulses, with these new attosecond technique, now to 65 attoseconds. And so, in principle, the time delay could go down to, without pulses overlapping, to about 65 attoseconds. Just an attosecond to make sure everybody knows it. I'm sure you would do, but it's 10 to the minus 18 seconds. So you can go to 65 times 10 to the minus 18 seconds. I mean, in principle, in practice, it's pump probe is kind of difficult yet. In the attosecond.
But how do they make this happen? I mean,
I showed
the time delay, you have to tune the distance for the pathway, but for the distance you have this speed of light which is equal to
That's exactly
the speed.
So it's easiest to see in one of these, like autocorrelation. Let's go back here to this one.
Yes.
So let's go back. I could have kept everything in this. This would have been good maybe.
So you take the pulse, so now the pulse, you divide it in two by taking it through a material and reflecting it off the material. If the pulse is very short, this gives dispersion problems, and so you need to correct this one as well. But that's a detail. Let's assume that the pulse is a true identical pulse after this. So now I go through a delay line, speed of light we know, and so if I need a little more time delay, I just add a little bit of length. And the lengths are kind of convenient. You travel a micrometer, right? A micron is the period of visible light, it's a couple of femtoseconds, right? So a micron is a couple of femtoseconds. So if I move a micron, I make a couple of femtosecond change. And so I can manipulate these pulses to overlap with the time accuracy. I can easily go submicron, so there's no reason why you can't do this very, very, very accurately on the time scale. Even on Attosecond time scales, you can do this very accurately. You can also find ways to do this which are common pathways, where you don't even have to worry about fluctuations. In a real experiment, you've got some error, and this mirror might move a little bit, and you can easily get a micron error. To get around that in a real experiment, you could feed back by using interferometers and try to correct this, or you can try to find ways to do it where everything uses the same path. And there are ways to do that. I can talk to you afterwards about that.
It just occurred to me, in these beam splits, are you splitting the fields or the intensity?
Well, you think about it as splitting the intensity, I guess, but is there a difference? We buy a beam splitter, it's 50-50 beam splitter, we think of the intensity, or a 30% beam splitter. I guess I'm not sure I understand.
No,
There would be a field version of that number, I guess, but I think intensity. I say intensity. So these are very convenient experiments to do because the delays are just appropriate. What is not obvious, I didn't make obvious, and that is, what if you want to change the pulse, the pump pulse frequency? I applied it in the other one. Turns out you can make continuum in between here, so you can change the color of this light without changing its time duration, almost anywhere you wish. But that's femtosecond technology, and I didn't choose to go that way, and I doubt any of the speakers will. But if you want to know about it, anybody wants to come and ask about how visible near the probe was done, I can describe a lot of it to you if you wish.
And I think you should, but before we sort of break for a few minutes, in order to stretch, I really need to stretch. And Ken sets up. I'd like to ask one question. I was intrigued by this thing you brought up about this few mini Atto effect. I think it was the phase matching issue that you brought up. So is this picture more closely related to a classical picture where each atom is an emitter and you do like a super radiance? You take the collective behavior of the atoms into account? Or should I look at it as a mini atom wave function picture? Which one is it? In order to be able to simulate?
I think of these atoms as randomly oriented, so I can't think of it. I think of
So
many atom
it would
picture.
be more of a classical picture as it's individual emitters.
Individual atom. What's
Influencing
what's good about harmonic generation, these nonlinearities in general, is the characteristic of the atom disappears because you go back to the same position. So I don't care where the atom is, everything is organized by the light, and the details of the atom are moved. If the atom changes, or if it's a molecule, if people do these experiments, if you excite a molecule, and let's say the nuclei just begin to move a little bit, now information is somewhere else. The phase is gone, and you've lost that contribution. And people do these experiments. You can watch the atoms move in a molecule just a little bit. They only have to move enough so that the wave function no longer overlaps the original wave function when you've lost harmonic convergence.
I have a follow-up question. So tunneling is a quantum effect, so there is fluctuations associated with your electrons.
Excuse me,
Tunneling is a quantum effect, so we imagine the fluctuations in the tunneling terms. Does it give the line width to your system, the additional line width? Or is your pulse so short that it's kind of a...
Yeah, the issues of the characteristics of the electron wave packet that are created in the longitudinal direction, in the direction in which it comes, are difficult to deal with. It's hard to get a hold of them experimentally. I don't think there's a clear experimental measurement. People worry about it theoretically, and there's all kinds of people that think about it. First, there's issues of tunneling time, and is it meaningful? So there's a great deal of research done on tunneling time. I mentioned the Atto clock. One of the ways to do it is the Atto clock. So let me just describe it to you under this context. So we have a molecule or an atom that wishes to tunnel. And you will find if you do the classical physics in circularly polarized light, if the field is pointing in this direction, the electron will go in that direction. You just work with the classical physics and you'll find. And so if it goes in that direction, you sort of do something about what direction it was in tunneling. And if you know the time, the field going around, you know the time. So you're starting to get time information, this direction in time, you know, the way direction the field is pointing. And so can you then put somehow information in here that looks at it? You could take a molecule where you know it should tunnel in this direction. Is it delayed? Or you could take an elliptically polarized light that tries to bias the tunnel in this direction. And is that bias a little bit off, for example? And these are argued to be related to tunneling time. And it's an interesting subject. I think personally, this is my own view now, I think in the single atom, a single electron, a hydrogen atom, there's no tunneling time, I think. Quantum mechanics is clear. That's my view. Maybe in a multi-electron system where there's more complex interactions and electrons just don't do what they're told to do right away. Maybe there is an interesting issue here. This is I don't work on it, so I only look at it from afar. That's my view. And so maybe you have a chance to look at interesting multi-electron.
No, I'm just curious because it's...
So, but you're still, I'm confused, we're still talking about quantum mechanics. I mean, we're describing these atoms or molecules with a quantum mechanical perspective. So...
It's incredible that classical physics takes you as far as it goes. It's amazing. But yes, of course it's a quantum mechanical process. It's really
we cannot,
an atom or molecule.
But I mean, my point is that we cannot say that this, like I don't understand the time that we describe here.
Well, my view, I think you and I would agree. I think in a simple case, hydrogen atom, so I don't have to think of it too hard, there is no time. Electron always exists underneath the barrier, and so it just comes out. There is no time. It isn't there.
So what happens when you have like more complicated atoms and molecules?
Well, maybe this is my naivete about complex systems. I think of an electron trying to be removed from a complex atom is interplaying and interchanging with the electrons that are there. And so the electron removal can easily interchange. It can excite another electron in the way out. There's a whole set of things that are involved, I think, in removing from a multi-electron. And so at least to me, I could imagine phase delays or things that look like atoms. And this would be a measurement in this more complex environment. That's what I think. Now, I told you I don't work in this, so I'm not an expert. I'm just giving you my view. So if you've got good ideas in this, I'd be happy to talk to you about it, because it's an interesting subject. So it's not that I haven't thought about it some, but it's not my field.
So this looks like a good opportunity for those who would wish to come forward.
Yeah,
but we
great.
will break out for a few minutes. There is some stuff, yes, to drink or eat. And then we will come back in very few minutes. Okay? Thank you.
Thank you very much.